The alert pulses through global astronomy networks at 3:17 a.m. GMT on June 12, 2025. A faint streak registers on the Atlas telescope array in Hawaii, flagged as an anomaly within seconds. By dawn, observatories in Australia, South Africa, and the Canary Islands are reorienting their lenses. This isn't a routine sighting. Within 48 hours, schedules are upended across 6 continents. Over 300 telescopes, from the Vera C. Rubin Observatory to backyard rigs in rural Japan, lock onto a single point of light moving against the stellar backdrop. This is no comet, no asteroid, not even a predictable interstellar wanderer. By June 20th, the designation hits level 5, an unprecedented priority in the annals of modern astronomy. Level 5 hasn't been invoked for Oumuamua in 2017, nor for Borisov in 2019, nor for any object in humanity's catalog of cosmic visitors. It's a classification reserved for phenomena that defy every model, stacking anomalies so improbable they demand immediate global action. The James Webb Space Telescope halts its deep field survey on June 25th. The European Southern Observatory's extremely large telescope pivots its 39-meter mirror. Even SpaceX's prototype Starscope, a privately funded infrared observatory, joins the fray. Amateur astronomers, wielding 16-inch scopes, coordinate via encrypted X channels, logging 24/7 observations. By early July, 5,600 precise positional fixes pour in from 312 observatories. This is a scientific mobilization unseen in our lifetime, a race against a fleeting window before the object vanishes into the galactic deep. The object carries a name now, 3I/ATLAS, the third confirmed interstellar visitor to breach our solar system. Its trajectory is hyperbolic, unbound to our sun, a one-way traveler from the Milky Way's vast unknown. It will graze the sun at 1.28 astronomical units in mid-November, then sling outward, lost forever by spring 2026. We have one shot to decode its secrets. But why level 5? Because 3I/ATLAS shatters every expectation of what an interstellar object should be. Its spectral signature is alien. Its motion defies physics as we know it. Its size strains statistical probability. And its path raises questions whispered in mission control rooms but never spoken aloud. This isn't just about science anymore. It's about confronting what we're truly observing before it slips beyond our reach. The clock is relentless, and the data is rewriting the rules. Astronomers measure interstellar objects against a rigorous scorecard, 5 key metrics that anchor speculation in hard numbers: non-gravitational acceleration, chemical composition, metallicity, orbital inclination, and outgassing onset distance. Each is a cold, objective test. Oumuamua in 2017 scored one anomaly: unexplained acceleration without visible gas jets. Borisov in 2019 was textbook: water-rich, carbon monoxide-driven, a predictable comet with zero surprises. 3I/ATLAS lights up the board like a warning signal. Its non-gravitational acceleration is negligible, less than 8 meters per day squared. Comets typically wobble under their own gas emissions, but this object holds steady, implying a mass far greater than expected. Calculations from early data suggest a nucleus 6 to 8 kilometers wide, larger than Comet Hale-Bopp, a giant among solar system comets. Statistically, finding an interstellar object this massive as only our third detection is like drawing a royal flush on the first hand. The odds are vanishingly small. We should have spotted thousands of smaller fragments first. The chemistry deepens the mystery. Spectra from the James Webb Space Telescope and ESO's extremely large telescope reveal a coma dominated by 92% molecular nitrogen, with water vapor barely registering at 4%. Typical comets are water-heavy, their comas glowing with H2O and carbon monoxide. This nitrogen dominance is unheard of. It suggests formation in a frigid stellar nursery, far colder than our Kuiper belt, where nitrogen ice could solidify while water remained gaseous. But even then, the ratio is extreme, unmatched by any known comet. Metallicity pushes the enigma further. Observations from the Keck Observatory detects strong cobalt signatures in the coma, but iron, its usual companion, is nearly absent. In nature, cobalt and iron form together in stellar explosions, sublimating at similar temperatures. Separating them requires precise conditions we replicate on Earth through industrial processes like cobalt carbonyl extraction. In space, such decoupling is virtually unknown. One preprint from Caltech notes, this metallicity profile resembles engineered alloys more than natural cometary dust. It's not evidence of artificiality, but it's a red flag that demands explanation. The orbital path adds another layer of intrigue. 3I/ATLAS enters at a mere 4.8 degrees inclination relative to the ecliptic, the plane where Earth, Venus, and Jupiter orbit. Interstellar objects should arrive from random angles, as Oumuamua did at 33 degrees and Borisov at 44 degrees. A near-ecliptic approach is statistically rare, aligning the object's trajectory almost perfectly with our planetary disk. It passes 0.22 astronomical units from Venus in October, skims Mars' orbit in December, and crosses Jupiter's path in April 2026. This alignment isn't impossible, but it's improbably convenient, offering multiple vantage points for observation. The final metric, outgassing onset, seals the anomaly stack. 3I/ATLAS was already active at 5.1 astronomical units beyond Jupiter's orbit when ATLAS first spotted it. Most comets remain inert until 3 astronomical units or closer, where solar heat triggers water sublimation. Nitrogen ice, volatile at lower temperatures, explains the early activity, but the sheer volume of the coma at such a distance suggests an unusually active nucleus. 5 metrics, 5 anomalies. Each could have a natural explanation: a massive nucleus for stability, an ultra-cold formation zone for nitrogen, rare chemical processes for cobalt, a dynamical fluke for the trajectory, and volatile-rich ice for early outgassing. But together, they strain probability to the breaking point. One oddity is notable: 5 demand level 5. Let's be explicit. No one is jumping to extraterrestrial conclusions. Science doesn't work on leaps. It thrives on tests. 3I/ATLAS is a puzzle, not a proclamation. Our task is to dissect it with precision, to show you the data driving this global sprint, and to outline the experiments that will cut through the fog. 2 tests stand out for their simplicity and power. First, spectroscopy of the coma's dust tail. Dust grains reflect light in distinct patterns based on their size, shape, and composition. By analyzing these patterns across multiple wavelengths, telescopes like Keck and Gemini North can map the grain structure. Typical comets produce fluffy, ice-rich dust. If 3I/ATLAS shows compact, metallic grains or unusual crystalline structures, it flags a composition outside known models. This test is fast, ground-based, and already underway. Second, astrometric precision via stellar occultation. As the object crosses background stars, its nucleus briefly dims their light. Observers worldwide, including amateurs with 10-inch scopes, can time these events. Multiple measurements create a silhouette, pinning the nucleus size to within meters. A single occultation event in late October could confirm whether this is a 6-kilometer Titan or a smaller, hyper-reflective fragment. These aren't speculative proposals. They're standard tools delivering hard numbers, and they're happening now. October 9th marks a pivotal moment. Venus aligns at 0.22 astronomical units from 3I/ATLAS, offering a unique observational angle. The Bepi-Colombo spacecraft, orbiting Venus for its joint ESA-JAXA mission, carries a high-resolution ultraviolet spectrometer. At 33 million kilometers, it can't resolve the nucleus, but it can dissect the coma's gas emissions with unprecedented clarity. One spectral scan could refine the nitrogen-to-water ratio, revealing whether deeper ice layers are shifting the chemistry as the object nears the Sun. Mars follows on December 14 at 0.17 astronomical units. The Perseverance rover, equipped with its Mastcam-Z, could capture coarse images of the coma from the Martian surface, a first for surface-based observation of an interstellar object. These planetary alignments are gifts of geometry, narrowing uncertainties that Earth-based telescopes can't resolve. By April 2026, 3I/ATLAS crosses Jupiter's orbit at 0.41 astronomical units. The Europa Clipper, launching in October 2024, might be in position for a distant pass, its instruments tuned to detect trace volatiles or magnetic anomalies. These aren't close flybys, but they're bonuses no one expected when the object was first spotted. On August 15, 2025, during a rare alignment with the Perseid meteor shower, 3I/ATLAS produced a startling visual. Its coma flared a vivid indigo, captured in long-exposure images from the Subaru telescope in Hawaii. Comets often glow green from diatomic carbon, C2, or cyanogen, fluorescing under solar ultraviolet. But indigo? Spectral analysis revealed a dominance of ionized nitrogen, N2+, a molecule rarely seen in cometary comas. The glow requires intense solar radiation in a nitrogen-rich environment, conditions 3I/ATLAS meets, but at an intensity unseen in solar system comets. A preprint from MIT noted, the indigo emission suggests a coma chemistry driven by processes we've only modeled in extreme stellar environments. Two explanations compete. First, the nitrogen ice sublimated early, ionizing under solar wind as the object approached 2 astronomical units. This fits the timeline, as water vapor increased in late August, suggesting layered ice reserves. Second, an unknown molecule could be contributing to the glow, mimicking nitrogen's signature. The August spectra are still under analysis, but the indigo flare underscores the object's alien chemistry. It looks like a comet, behaves like a comet, but its ingredients read like a dispatch from another star. Picture the nucleus as a cosmic archive, its ices and metals frozen records of a distant stellar system. Nitrogen ice forms the outer shell, sublimating first under faint solar heat. Water and carbon compounds lie deeper, emerging only as the object nears perihelion. Cobalt, decoupled from iron, hints at a formation environment with unique temperature gradients or chemical sorting. This archive tells a story of a star unlike our sun, perhaps older, metal-poor, or surrounded by a disk where nitrogen dominated over water. Every spectrum we collect is a page from that archive, revealing conditions billions of years ago in a corner of the galaxy we'll never visit. 3I/ATLAS isn't just a rock, it's a chemical time capsule, and we're racing to read it before it fades. Level 5 isn't a label, it's a mandate. It unlocks resources that redefine priorities. The James Webb Space Telescope, with observation time valued at $10 million per hour, broke its queue within days. The extremely large telescope delayed exoplanet surveys. Starscope, SpaceX's experimental platform, diverted from its dark matter baseline. This kind of pivot demands extraordinary justification, and 3I/ATLAS delivered it with its cascade of anomalies. Level 5 also triggers rapid response mission planning. Engineers at JAXA and ESA modeled intercept trajectories using existing spacecraft. A bold proposal emerged in July, redirecting Bepi Colombo for a distant flyby. The spacecraft, already at Venus, could burn its remaining fuel for a trajectory shift, intersecting 3I/ATLAS at 50 million kilometers in November 2025. It's a long shot, fuel margins are tight, and the science return is uncertain, but the fact it's on the table shows the stakes. Level 5 means no one hesitates. Every hour of observation, every redirected instrument, every calculated trajectory is a bet on discovery. Not panic, not hype, but relentless curiosity drives this moment. The cobalt anomaly demands a closer look. In every known comet, iron and cobalt coexist, forged in supernovae, embedded in dust, and released together as the nucleus warms. 3I/ATLAS breaks this rule. Keck's spectrographs, operating in June, confirmed cobalt vapor in the coma, but found iron lines faint or absent. This separation mirrors industrial processes on Earth, where cobalt is purified using carbonyl chemistry at specific pressures and temperatures. In space, a natural analog exists. Cobalt carbonyl molecules could form in a nitrogen-rich, ultra-cold environment, volatilizing cobalt while iron remains bound. It's plausible but rare, requiring a formation zone unlike anything in our solar system. A team at Oxford noted, this chemistry suggests a parent star with a radically different metallicity profile. The anomaly doesn't scream artificiality, but it whispers of a birthplace so alien it challenges our models of cometary formation. It's a clue to a stellar nursery we've never sampled, a puzzle that demands more data before the object slips away. The trajectory's near-ecliptic path sharpens the focus. At 4.8 degrees inclination, 3I/ATLAS threads our solar system with precision. This alignment enables Venus, Mars, and Jupiter observations, but it also raises questions. Is it chance? Interstellar objects should arrive isotropically from any direction in the galaxy. A near-ecliptic entry suggests either a dynamical bias, perhaps objects from the galactic plane align with ours, or a statistical fluke. The sample size is small, 3 interstellar objects total. We can't yet map their distribution, but the alignment maximizes our observational leverage. Venus's proximity in October allows Bepi-Colombo's ultraviolet scans. Mars' December pass lets Perseverance contribute. Jupiter's April 2026 window could involve Europa Clipper. Each angle refines our view, from size to composition to dust dynamics. Coincidence or not, this path is a scientific goldmine, and we're mining it with every tool available. Could a spacecraft reach it? The Bepi-Colombo proposal, published in a Nature Astronomy preprint, outlines a feasible but daring plan. A maneuver in early October 2025 could reposition the spacecraft for a November encounter. At 50 million kilometers, it's not a close flyby, but Bepi-Colombo's instruments could detect gas emissions, magnetic fields, or dust properties invisible from Earth. The trade-off is steep. The maneuver would end Bepi-Colombo's Venus mission, consuming its fuel reserves. The science case is compelling, unprecedented data on an interstellar object, but the decision rests on risk versus reward. If approved, it would mark the first targeted interstellar intercept. If not, it underscores a gap in our capabilities. A dedicated rapid response probe, perhaps a 250-kilogram craft with spectrometers and a high-gain antenna, could be built for $200 million, ready to launch within months of a future Level 5 alert. The lesson is clear. We need to be ready for the next one. What would silence the skeptics? Not speculation, but evidence. 4 tests could shift the paradigm. First, radio emissions. If 3I/ATLAS emitted narrowband signals tied to its Doppler shift, facilities like the Square Kilometer Array would detect them. So far, silence. Second, light curve anomalies. A non-natural object might reflect sunlight in sharp, periodic glints, unlike the diffuse scattering of a comet's rough surface. Photometry from Gemini North shows no such glints yet. Third, non-gravitational thrust decoupled from solar heating. If 3I/ATLAS accelerated without correlating to its coma activity, it would challenge natural models. Current data show minimal acceleration consistent with its mass. Fourth, isotopic ratios. If the nucleus harbors carbon-12 to carbon-13 ratios far outside solar system norms, it confirms an alien stellar origin. These tests are active, their results accumulating weekly. They don't assume answers, they demand them. Why does this matter beyond the headlines? Because 3I/ATLAS is a Rosetta Stone for the galaxy. Its nitrogen-heavy chemistry hints at exoplanet atmospheres we've never modeled. If nitrogen dominates comets in certain stellar systems, it reshapes our search for habitable worlds. Its dust properties inform spacecraft shielding for interstellar missions. High-velocity grains like those in 3I/ATLAS's coma test materials we'll need for voyages beyond the heliosphere. Its trajectory refines rapid response protocols, critical for planetary defense against rogue objects. Every spectrum, every measurement shrinks the unknown. We learn what chemistry is possible, what environments birth comets, how to distinguish the ordinary from the extraordinary. This isn't just about one object. It's about equipping humanity for the next cosmic encounter. 5 numbers define the story. Inbound velocity, 72 kilometers per second, too fast for solar capture, confirming its interstellar origin. Perihelion distance, 1.28 astronomical units, close enough to trigger outgassing but safe from Earth. Nucleus size, 6 to 8 kilometers, a statistical outlier for early detections. Nitrogen to water ratio, 92% to 4%, unprecedented in cometary records. Ecliptic inclination, 4.8 degrees, a near-planar path maximizing observation. These metrics are the scaffolding of the mystery, grounded in data refined daily. The campaign accelerates now. October's Venus Pass brings Bepi Colombo's data. December's Mars alignment adds Perseverance's view. Occultation events through November pin the nucleus size. Radio telescopes scan for signals. Post-perihelion spectra, expected in January 2026, will reveal deeper ice layers. Each milestone tightens the net around the truth. 3I/ATLAS is a fleeting visitor, but its lessons endure. It challenges our assumptions, sharpens our tools, and reminds us that the universe is vast, strange, and full of surprises. We've delivered the promise, a level 5 alert, its anomalies laid bare, its tests outlined, its stakes clear. The nitrogen coma, the cobalt puzzle, the ecliptic path, all verified, all measurable. The global scramble is real, from professional observatories to citizen scientists. The tests are underway, from spectroscopy to occultations. The implications span exoplanet science, spacecraft design, and planetary defense. This is humanity's response to the unknown, methodical yet urgent, curious yet disciplined. As 3I/ATLAS nears the sun, every observation counts. What will it tell us about the galaxy's depths? What will it reveal about our place in it? Stay curious, share the journey, and let's uncover the answers together.